Next, we move on to visualization with like importing matplotlib as PLT and importing seaborn SCN. Then we have define, detect outliers, IQ, interquartile range, data, and column. Basically, this defines like an outlier detection function using like the interquartile range method. Then we have Q1, Q3 till data column. The quartile is equal to brackets 0.25 and 0.75. Basically, this calculates the 25 percentile of Q1 and the 7th percentile of like Q3. Then we have IQR is equal to Q3 minus Q1. Basically, this calculates the interquartile range, which is like the middle 50% of the data. Then we have lower and upper is equal to Q1 minus 0.51 times interquartile range, Q3 plus 1.5 times interquartile range. Basically, this defines like the lower and upper outliers of boundaries using the 1.5 times IQR rule for the data set. Then we have outliers equal to data.column less than lower, and data.column is greater than upper. Basically, what this does, it filters out the data to find like the values outside of like the normal range. Then we do return length outliers, length outliers divided by then data times 100 basically returns a count under percentage of like the outliers. Then we have outliers analysis is equal to brackets, then key columns is equal to income annual all the way to like commercial asset value. Basically, this allows us to like analyze outliers like in key financial features such as like income all the way to commercial asset value. Then we have for column in key columns. Basically, this loops through each of the financial features. And then we have count percentage is equal to detect outliers IQR, df process.call. Basically, this applies the outer detection function to the current column. Then we have outer analysis column is equal to count percentage percent. Basically, this stores the results in a dictionary for like later use, and afterwards we display the immediate feedback on the outlier appearance by this line of code over here. Then we move on to visualizing with boxplot for outlier detections by basically using a for I in column and numerate key columns, and then making a box plot with the data is equal to df process, y is equal to column, and axis is equal to axis I with the title and the tick parameters of axis y and label size a, and then we plot it over here. So here's our graph. So outlier analysis IQR method, income annual 0 outliers, loan amount is 0 outliers, and resident asset value has 52 outliers, which is like 1.2%. Commercial asset value is equal to 37 outliers with 0.9%. Here's our graph, outliers in income annual. Basically, it has no 0 outliers in this visualization as supported by here. Then there is no outliers for like outliers in loan amount. Then, however, there are outliers in the residual asset value as shown over here, and then there are outliers in the commercial asset value as shown over here. So yeah. Next, we move on to visualizing the distribution analysis and feature relationships. So first, we've visualized the income distribution by loan status by using like a histoplot with the data of df processed, x is equal to income annual, hue is loan status, bin is 30, and alpha is 0.7, and x is equal to 0 with the title and x label. Then we visualize a loan term with income by approval status, in which we create a box plot with data of a data process, x equal to loan term, y is equal to income annual, hue is equal to low status, and x is equal to axis 1. Then we set the title, the x value, and the y value, and then we plot the both. So here's our visualization for both. Here we have the income distribution by loan status. So as we can see from the graph that people with higher annual incomes, which is like the dark blue over here, which is the light blue over here, have a higher like approval rating of an approval status as people who are rejected, who have like a lower annual income, which is like the dark bluish over here. Then we have like the income distribution by loan term and status. So people who have like higher incomes are more likely to be approved by the loan. As you can see the range between like the approved and rejected for each, as the blue one is bigger than like the orange one. Basically, what these two graphs shows is that higher income applicants have like a higher, better approval rates across like all the long-term loans. Next, we move on to outlier treatment using a log transformation and capping method. So we begin by importing warns, and then df is equal to df.copy. Basically, this creates like a new data frame for the outliers treatment experiments, and this is preserves like the original process data and allows comparison between like different treatment methods. The first treatment method we have is long transformation for skewed features. So long calls is equal to income annuum all the way to commercial asset value. Basically, this selects like all the financial features that have like that typically have skewed distributions. Then we move on to for call and log calls. Defined treatment is equal to f.call equal to np.log df treated brackets call dot absolute plus 1. Basically, what this block of code does is it takes like the absolute value to handle any negative values and applies like a log transformation by using np.log and creates like a new column with the log suffix, and this reduces like the skewness as it is and allows for compression of like larger values more than like smaller ones. Then we move on to method 2, which is Windsorization, which is capped at the 5th and 95th percentile. So we have for call and log calls, lower and upper is equal to df.treated brackets column for quotile 0.05 and 0.95. Basically what this line of code does, it basically finds the 5th and 95th percentile values as it's like defined as like the normal range and basically exclude like the extreme 10% of the entire data. Here, then we move on to which warning, catch warns, warning, thou simplify, ignore, future warning. Basically, this suppresses like future warning for cleaner output within like Google Colab itself. Then we have clipped values is equal to df.treated brackets call, and clipped lowers is lower and uppers uppers. Basically, what this line of code does is it caps the values at the 5th and 95 percentiles, as this reduces like extreme outliers while preserving the data's distribution overall. So yeah. And then we have df.treated call and when zerd equals to clipped values as type data df.treated call and type dt. Then we move on to printing out the log transformation with the applied with length log calls features, and then Windsorization applied to length the log columns features. Then we move on to comparing a distribution for like the original versus long transform versus Windsorized. So here are the histogram for the original long transform, then Windsorization, and here are the blocks plot for the original long transformation, long transformed, and Windsorization. So here's our visualization over here. So in the original income annuum, basically this histogram shows like a normalish like histogram distribution, while however the long transfer income annuum has like a left skewed basically distribution, while as compared to like the Windsorized income annuum, which is similar to like the similar to like a normal distribution but with extreme values capped at over here and over here. Then we have like the original box plot, the log transform box plot with outliers over here, and then like the Windsorized box plot over here. There's few numbers of outliers in like the first and third box plot as compared to like the third one, which has like a lot more than the other two. So yeah.